Okay, I think the recording has started. So I hope that you were able to see me and hear me and also see the screen. So this is an extra session of the problem solving sessions in this course. So last time we were not able to discuss many problems because we discussed other things which were requested by you. So in this session, we will only discuss problems which are related to the assignments of this week, which has deadline on this Wednesday. So in the process, we will learn something called non-wasteful NV-free allocations. So without further ado, let's start. Okay. Okay, so in this problem of non-wasteful NV-free allocations, you have a set of n agents. So there are n agents are nothing but people, persons, and m objects or items which you want to allocate to this n agents. So consider this example. So there are 5 persons and there are certain number of objects. So number of objects could be much more, many more than the number of persons. So one person may get multiple items, and we want to assign the items to the persons such that we assign items. So every person is assigned items that he or she values positively. Okay. So we have an utility matrix. So this utility matrix is showing which person likes which items. So for example, person one likes item one. Therefore, the matrix entry U11 corresponding to person one and item one is 1. So whereas person one does not like the guitar, which is item 2, therefore U12 is 0. He likes the mic, so U13 is 1. He does not like the notebook, so U14 is 0. He likes the radio, therefore U15 is 1. He does not like he likes the clock, so U16 is 1. Okay. So if you allocate an item which a person doesn't like, for example, if you allocate this notebook to this person, then that is just a waste because this person does not, in the perception of this person, the notebook carries no value. Okay, so we would like to avoid such allocations. And what we would like to do is we would so first property is non-wasteful. Non-wasteful meaning that everyone gets items that he or she likes. Okay. The second property is envy free. So envy free, as you can probably guess, means that you assign the items in a way that no person is jealous of another person. So we will define that formally. So it means that uh, an allocation should not be such that so once you do the allocation, so consider person one. So person one has received certain items. Okay, I don't know. And person two has received certain items and so on. If there are n persons, so there are lists of items allocated to this n person. So once the allocation is done, so every person gets to look at the set of items obtained by other persons. Okay, so the set of items that person one has been allocated is called bundle one, so B1. So the set of items that person two has been allocated is called bundle two, bundle of items, likewise till Bn. So person one gets to see bundle two, bundle three, and bundle n, and he should not feel jealous by looking at any of the bundles. So the utility of any of these bundles should not be more than the utility that he has obtained due to his allocation. That is the informal meaning of envy free. But let us go further and we will see things in a more formal way. Yeah, I'll make it slightly bigger. Maybe this needs to be slightly zoomed in. So we define for every item, we define something called a fingerprint. We have a function called fingerprint, which acts on an item. So fingerprint of an item is nothing but the set of persons who like that item. Okay. So here they're saying,
So what about the quantity of the different items?
yes, so if you give 5 copies of an item that a person likes, then that person derives an utility of 5. So every item is value worth 1 utility. So if you give 5 items, that is utility 5.
So do we have unlimited supply of the item 1 and the item 2 and item 3? Like, do we have unlimited supply of the notebook, or do we have limited number of the notebooks available which can be distributed among the different persons?
So it will be specified that how many copies of an item is available.
Okay, okay.
So it will be specified in the given problem. So the question is valid. So the answer is however many items you allocate to the person, you multiply that number with the utility of that item, and utility in general is either 0 or 1. So a person either likes an object or doesn't like an object. There is nothing in between. So the utility is additive, and therefore you multiply the utility with the number of objects that you assign. Okay. So here we have understood what is fingerprint. So here's an example. So it is saying that so here's a camera. So camera has fingerprint person 135. So that means camera is liked by person 1, 3, and 5. Okay. So let's look at it. So camera's column is this. So in this column, which entries are 1? So this is an 1 entry. So person 1 likes the camera, person 3 likes the camera, and person 5 likes the camera. Therefore, it is saying that camera has a fingerprint of these 3 people. Okay. Similarly, for the mic and for the radio, let's look at the guitar. So the guitar is liked by person 2, 3, and 4. Is that so? 2, 3, and 4. These 3 entries are 1 in this column. So that is correct. Similarly, for the clock, only person 1 likes the clock, and everybody else uh, assigns 0 value. So basically, everybody else has no utility for the clock. They don't want the clock. Okay. So this was some notation. So the ILP formulation we'll see later. So now we'll look at some variables. Let's make it slightly larger. So in the previous class on Friday, day before yesterday, we have seen the integer linear programming formulation for the vertex cover problem. So here they are going to do an integer linear programming formulation. So therefore, every variable that they will define will either get a value of 0 or 1. So ideally, when we are talking about integer linear programming, the values of the variables should be integer. But in this case, it is binary, that is 0 or 1, but nothing in between. So you do not allow a fractional value to be assigned to a variable. And now we want to formulate an integer linear program that represents this problem of non-wasteful NP-free allocation. So to do that, first we have to define some variables. So they are defining variables with respect to the persons. So there are 5 persons. So there are variables with respect to 5 persons, and there are 3 distinct fingerprints. So remember that fingerprint is with respect to an item. So we have seen that there are 6 items. So 3 of the items have same fingerprint. person 1, 3, and 5, they like item 1, item 3, and item 5. So with respect to item 1, the fingerprint is this, and with respect to item 3, this fingerprint is identical to that of item 1, and so on. So there are there are 3 distinct fingerprints with respect to these 6 items. So with respect to every fingerprint and every person, you define a variable. Okay? And these variables, they have given some values. So what these variables mean uh, is that, so before we understand what these variables mean, we have to formulate the LP. So let us now just count the number of variables, because in the next question we will formulate the LP. Then it will be easier to look at the constraints and sort of understand the full LP. So for now, just remember that the number of variables in the LP is going to be the number of persons or agents times the number of fingerprints. So corresponding to every person and fingerprint, there is a variable. Now, how these variables are assigned, we will see. Okay, fine. So this was some notation. So now we look at the question. So without these notations, we wouldn't have been able to appreciate the question. So now let's look at some questions. Okay. Yes. So yeah, so here is an ILP formulation. Okay. Just a second. I'm looking at the ILP formulation. So this is a slightly different ILP formulation for this question. So actually, this ILP formulation is with respect to the assignment that is due on Wednesday. So I should not say anything beyond what I have said for this, because this is the deadline is yet not over. But we'll look at a similar ILP formulation. So let's look at this question. So this question is not part of uh, the immediate assignment that we have. So I'll give you a minute or so to read the question. So we have a set of agents. So agents are nothing but people, and there are m items to be distributed, and each of the items have multiple copies. So the ith item has mi copies, and each agent has an utility for the items. So you can assume that either a person likes an item or a person doesn't like an item. So UA is a utility function from the set of items to the set of integers. So U sub A. Just a second. So what is A? So A is an agent. So once you fix an agent, then for every item you have an utility. So here the utility is not 0 and 1, utility is an integer. Okay. So for every item there is a integer utility. So once you fix an agent, so you can define something like UA of an item to be some number. Let's say set of I don't know. So what is an allocation? An allocation is a partition of the n. So look, there are n agents. So let's draw it this way. So let us say we draw n boxes. So every box corresponds to an agent. So this is box 1, box 2, box 3 up to n. Okay. So you put some of the items in box 1, some of the items in box 2, some of the items in box 3 like that. So what all you have? M items. So an allocation A is nothing but a partition of these M items into n boxes or sets. And each box is for an agent. The utility that an agent I derives from his partition AI. So the ith partition has the ith box AI. So these there are some items in this box, and if a person, so the utility that a person derives from his box is the sum of the utilities of the corresponding items in his box. An allocation A is said to be dominated by another allocation X if under X. So this is one allocation. There could be another allocation. So maybe I'll just put some numbers. So maybe this is item 1 and item 4. This is item 2 and item 7, like that.
So is this a coincidence that we have the same number of the items and the same number of the agents? Basically, this allocation thing is not clear, that this allocation is defined as a partition of the items into the n number of the sets. So we have been given n number of the sets, and we have same number of the agents as well.
No. So number of boxes is equal to the number of agents. So every box is corresponding to an agent. So first box is for agent 1, second box is for agent 2, the third box is for agent 3. So therefore, because there are n agents, so there are n boxes.
Okay, and what this mi here stands for, the small mi?
All in mind.
In the very first line, it is given that the m
Oh,
number
this is
of.
multiplicity. So that every item, so the ith item has mi copies. So the ith item is a notebook. There are mi notebooks in the supply.
Okay, and all these summation of the mi would be equals to the capital M.
No. Capital M, a set of item types M. So M is the total number of types of objects. So
Okay,
in this case, previously we have seen there are 6 types of objects. So here M is equal to 6 and N is equal to 5.
mhm, mhm. And this A5, A3 would refer to the number of the items which have been allocated to the agent 3.
It is the set of items,
Uh-huh.
maybe 3 notebooks and 1 guitar and 2 mics like that. That is a box. He has a box, and in his box there are a set of items.
Okay, okay. And so what will be the utility for the allocation for the agent 3? That will be equal to the sum of the utilities given
Yes.
for the item in the box A3.
Yes. So we have the utility matrix like this. So look at that. What are the values that the person assigns to each object? So the utility is 1. So we say, okay, 1 into the number of objects of that type. And if
Yeah,
there is no utility, then we say, okay, however many guitars are there, person 1 is not going to care about it.
T. Yeah, fine.
So So that is how a partition or allocation, sorry, that is how an allocation is done. So there could be multiple allocations. So one of the allocations, so how are we going to compare the allocations? So if it so happens that in one allocation, somebody achieves more utility than in the other allocation, and everybody else is achieving the same allocation, same utility, then we are going to say that so there is a domination relationship between the two allocations. That is what this sentence is saying. An allocation A is said to be dominated by another allocation X if under X there is at least one agent who receives strictly greater utility than he got under A. So that person has to receive more utility under the new allocation, that is allocation X, and no agent gets lesser than what she got under A. So we are comparing the utilities of the entire set of people. So we have n people to allocate stuff, and one allocation is strictly better or dominates another allocation if there is at least one person, there is at least one agent who receives strictly greater utility than he got under the previous allocation. And in that process, so what that means that in this new allocation, this person we are concerned about receives a different set of items, or maybe more items when a multiplicity of items have increased per type. But in that process, other people will get different set of items or different number of items. But it should not happen that while trying to increase the utility of this person, we have decreased the utility of the items allocated to another person. So if that is the case, then we will say that there is this allocation A which dominates, sorry, allocation X dominates allocation A. So allocation A is said to be dominated by another allocation X. Okay. So formally, there exists an agent A such that what is X sub K? So X sub K is a box corresponding to the person K under the allocation X. So if you take the sum of the utilities of the items allocated to this person K under the allocation X, that utility is strictly more than the sum of the utility of his box, that is AK. And for every other person, every other agent, I not equal to K, the utility every other agent is getting under the new allocation is no less than the utility he or she was getting previously. So the definition of domination is this. So is that fine? So the point of defining this domination relationship between two allocations is that, so given an allocation, so we want to ask that question that whether there exists a better allocation that dominates the given allocation. And if there is no such dominating allocation, then we will say that, okay, we cannot do better. So that kind of allocation, where we cannot increase the overall utility, we cannot give anybody any better utility. So that kind of allocation is called efficient, or more formally, there is a name. It is called Pareto efficient. Okay. So this is the term people often refer to in game theory. So if you have no doubts, then we can move on. Otherwise, I can repeat it. Then we can look at the question.
Yes, so the problem formulation is clear.
Okay. So let's look at the questions now. So let's define some variables. So the number of items of type I that allocation X assigned to an agent is denoted by X sub A super I. So X sub A super I means that the agent A is receiving items of type I under the allocation X, and the number of such items is X sub I super A. Then we have to answer a couple of questions. So there is a question on ILP formulation also. But before that, let's number them A, B, C, D. There is an E also. So the first one is asking, so if there is an allocation X that dominates A, so X is strictly better than A in terms of our definition, then is this true? So what does it say? So it says for every agent, so N is a set of agents. So for every agent A, the summation over all the items. So basically we are looking at the row corresponding to, so we are looking at the utility matrix. So there is a row corresponding to the agent A, and these columns are for the items. The M items are there. We are looking at this row. So we are asking that if you consider the utility of the ith item for the agent A times the number of such ith, so number of ith item allocated to A times this thing. So this is the total utility agent A is deriving from the items of type I. So this term is a total utility that the agent A is deriving from the ith item. This is the multiplicity of how many ith items are assigned to agent A. So what is this total sum? So this total sum is nothing but the sum of the utilities obtained from all the items. So this is the total utility under the allocation X for the agent A. So if there is an allocation X that dominates A, then this total utility under X has to be greater than equal to this thing. So what does this thing mean? So what is A sub A? So A is an allocation. So A sub A is defined here. Okay, so A sub is the box corresponding. So A sub is the box corresponding to agent A under allocation A. So this is the total utility of the box that agent A has derived under allocation A. So this is nothing but the same thing. So the left hand side and right hand side are the same thing, but under two different allocations. Is that correct?
So because here equality is a part of this inequality, so quite possible that the allocation X could be as good as the allocation A is and may not be strictly greater. I mean, may not be strictly better in some sense. So
Yes.
therefore, this statement cannot be true.
So what you said, can you repeat what you said?
So I said that for the allocation, I mean under the allocation X,
Okay.
the derived utility is greater than or equals to. So what if the
Yes.
derived utility is equals to the utility of the partition A? So if both are equal, since equality is here, is a part
Mhm.
of the question.
Okay, you are saying because there is an equality, so this is not true.
So yeah, so it is not necessary that one of the utility of one of the item is one of the yes. So how do we establish the dominance that at least one agent who received? But now since we are focused on one particular agent, small a only, this is so this inequality is specific to the agent small a only. So yeah. Uh, So, but yeah, so this is for the this is specific, but then it is given in the question that for all the A's, which is the element of the capital N, so this thing should be true for all the agents. So
Yes,
therefore, yeah, this statement cannot be true. I mean, some of the agents, at least one of the agents, should get better value.
correct. That is true. So, right. So how do I rephrase it? So let me do it in a different way. So consider, so let me give you a different example. Okay. So I'm just making up the example. So let us say that you have, so let us say you are applying for jobs and you have two different job offers. Okay. So one from company X and the other from company A. Maybe different color. So you are going to prefer company X over company A if salary offered by company A, let us define it this way, or rather company X is strictly more than the salary offered by company A. Okay, let us say that is your preference rule. Okay, so now I give you a statement that if you preferred X over A, then the salary that A offered, or sorry, the salary that X offered is at least greater than equal to salary that A offered. So do you think this is correct? Maybe it is given more salary, but to say that more than equal to, is that correct?
So what if the salary of X is equal to the salary of A? Then
Yes.
the first thing that I give the preference to X over A uh, won't be true.
So let's take numbers. So let us say salary of X, I don't know, I'm just taking some numbers, 101, and salary of A, let us say, is 100. So now you are going to prefer X because that is a rule, because 101 is strictly greater than 100. So now you have told somebody that, look, I have already taken offer from X. So that person, can that person make an implication? So can that person make an assumption, or can that person make a conclusion that definitely the salary that X was offering was at least the salary of that A was offering?
No, the salary of X should be greater than the salary of A. There could not be an equality thing here, because salary is the only parameter of making a shift.
But is this true or not? Is it
Yeah,
true or false?
this is true, but then this is, I mean, this is not probably in this example it is true, but in the given question, since it is the question of the dominance,
Okay.
so for the dominance, the salary should be strictly greater than the salary of the person which he is receiving in the current employment.
Okay, then let's forget the salary example. So let's only talk about dominance. So ultimately it boils down to whether something greater. So ultimately it boils down to whether this is true or not. So let us rephrase. So here is a statement. If so, the statement is there is an allocation X that dominates A. So let us say this statement is P and this statement is Q. So whether P implies Q or not, that is the question. Then means, so that is the question. So for every agent, so it is saying that for every agent, so if somebody has said, told you that allocation X dominates allocation A, that implies that for every agent, this is true, that the utility obtained by each member agent under X is at least the utility obtained by each member under A. So one person has definitely got more, that is true. But
Uh,
does P imply Q? That is the question.
no, because I mean, Q includes a possibility wherein the equality holds true for all the values of small a. I mean, for all the small a's. This
So
includes
let it
that possibility.
let it be equal. So
So
but
if
Q
so
does
if
not, I understand Q does not, if the question was whether Q implies P, that would have been false. But whether P implies Q, that is the question. The question is not so what you are thinking, I understand now. So you are saying that Q implies P is false. That is 100% true. That is true. This so if you somebody says that okay, maybe all the agents have derived equal utility under the new allocation X, then the domination relationship you are claiming is not true. P is not true. That I understand. So Q implies P is false. But does P imply Q? That is the other direction of the question.
Yes, so fine. So let us say the negation of Q then. So if I take the negation of Q, then I mean, then there would be at least one A for which the utility of X is smaller than this, the utility of A. Because if P implies Q, then this implies what? The negation of Q or P? That
The
sort of the
negation
thing.
of Q will imply negation of P.
No, no, not this one. Say if P implies Q is given to us, then that would be equivalent to of what? The negation of P or Q. Okay, okay. Yes, so yeah, so yes, so if I take the negation of contrapositive, then there exists at least one agent whose utility is greater than this. So then this will imply that the allocation X does not dominate the allocation A. Yeah, so it
Exactly.
seems right. Yeah, now
Yes.
understand. Yeah, makes
So
sense.
not Q implies not Q, right? So that
Yes,
means P implies Q.
yes, right.
So this one is true. So we'll just mark it true. This one is true. Okay. So let's move to the next one. So an allocation X dominates A if and only. So this won't be true. That we have already agreed that P implies Q is correct. So this Q is same as this Q. Observe this. So P implies Q is correct, but Q implies P is not correct, right? So if and only if means P implies Q, this implies this as well as this implies this. That won't be correct. Why is that so? As you have said, that okay, maybe everything is equal, then X cannot dominate A. Maybe the utilities are all equal.
Yes.
False. So what is the next one? An allocation X dominates A. Again, there is a if and only statement, but this Q part, the condition, the other statement Q part is different. So let us parse this statement. Saying, so you take a sum over all the agents. Of sum over all the agents, and then sum over all the items. Then the utility that an agent obtains from an item multiplied by the number of such items assigned to this agent. So this is the sum of total utility per agent. So this is the sum of total utility under the allocation minus, what is this thing? This is utility for agent A because A is the box corresponding to agent A under allocation A. So this is the total utility of all the objects. Okay, so it is saying that if an allocation X dominates A, then okay. So again, so this is the difference in the total utility, and that has to be strictly positive.
Yeah, so it is true.
So P side implies Q side, that is immediate. So P implies Q is immediate. So I will mark that, okay, P implies Q is true. But what about Q implying P? Is that true?
So if this difference is positive, so yeah, so if this difference is positive, then it is not necessary that X will always dominate A. Quite possible that some of the agent may be receiving less utility and the
Yes.
other one may be getting quite high utility, thereby making the difference positive.
Yes. So it can happen that there is an agent which was getting 100 rupees worth item under allocation A, but now we were very biased and we gave him too many items, so he got 200 rupees. But in the process, some of the other agents might get very less amount, but even then the overall utilities difference could still be positive. So therefore, if the domination has to be true, then nobody should suffer in the process of increasing the utility of one person. So it has to be equitable. It has to be distributed equally, or rather, it has to be distributed justifiedly. So, but that may not happen. Just by this condition, it is not clear that whether everybody has got equal or more profit or utility under the next allocation. So Q implies P is not true. So therefore, if and only if is not going to be true. So this we are going to mark false. Okay, now we come to the ILP formulation. Okay, so now question is, now you know what are the variables. So the variables are nothing but this xi is. So xi is corresponding to the number of items of type I that has been allocated to agent A under the scheme X, under the allocation scheme X. So what are we maximizing? So this term is nothing but this term. So we are maximizing this utility difference. So where does A come from? So A is, let us say, an allocation called A is already known. So therefore, this ILP formulation is with respect to this allocation A. So you're saying that, okay, look, we have an allocation A. Under this, we know that what are the utilities that people have obtained. Now we want to give you, we want to find out an allocation X, which is strictly better in terms of total utility. But as we have seen in the previous problem, the domination thing has to work. So therefore, what are the constraints that should be there? So objective function is just the difference of utilities between allocation X and A.
So what's the meaning of the second constraint? The first one is fine, that the items allocated to the agent A should be less than or equals to the MI. That is what the meaning of the MI is, that the items allocated to, so what this MI here is, MI is the number of
It is
the
the number of
copies.
copies of
Uh,
item I. So it is saying that if there are only MI copies available, let us say MI guitars are available, then you
uh,
cannot give more than MI guitars to an agent A.
yes, yes. And what's the meaning of the second one then?
Second one means this is the second one.
Yeah,
So I'm talking about this one only. So this one says that if there are MI guitars, then any agent can get anything between 0 and MI guitars.
right. Then what would be the meaning of the first one?
The first one is saying that if you take the, okay, first of all, you fix an item I. So there are M items, so there are M constraints of this type. So once you fix an item I, then you take the sum over all the agents and the number of items of type I allocated to these agents, the sum of the items allocated to these agents of type I cannot exceed mi because there are mi items available at the most. So it is not necessary that an item, so let us say 10 copies of guitars are available. So maybe 2 guitars are given to agent 1, 5 guitars are given to agent 7, and 3 guitars are given to agent 10. So the overall sum of guitars that you have distributed cannot exceed the supply.
Yes, so I mean both the constraints are uh, referring to the same thing. In the second case, this is for all the values of a, and in the first constraint, the submission has been taken over the a. So
Yes,
wouldn't we referring to the same thing, one and the same thing? That the number of the
that is true.
items.
Yeah. So you are saying that the second constraint is redundant because of the first constraint.
Yes, because if I have been given 10 number of the items of a guitar, then the total distributions of the guitar across all the agents should not exceed 10.
Correct. Correct. So you are right. But when this thing is probably necessary that you do not allow negative values of a variable. So that this part is necessary. That the number of items you have given to an agent is non-negative.
Yes.
So but you can understand that the problem that we are trying to solve is not fully expressed by these two constraints. So maybe we need some more constraint. So let's look at the next option. So this one is saying the same thing, that the objective function is to maximize the difference of utilities under the two schemes of allocation A and X. And these two constraints are the same, that you do not allow more allocation than the available supply. So there's an additional constraint, whether it makes sense or not, let's look at it. So it is saying that consider an agent. So for this agent, you take the sum of all items, and this is the utility obtained by this agent if the ith item is allocated to him. And this is the multiplier, that how many items of type I has been allocated to him. So this is basically the overall utility the agent A has obtained. On the left hand side, we have the overall utility that agent A has obtained under the scheme allocation scheme X. And on the right hand side, so AA is nothing but, as we said, the box corresponding to agent A under allocation A. So the utility obtained uh, under the scheme A is this thing. So this one is saying that, okay, that domination, this is the domination constraint, that every agent has received at least that much utility under X that it has received under A. So it can happen that if we solve this ILP, then we may get an allocation X. Uh, so if we maximize, so if we maximize this quantity and this maximized value, this objective function value turns out to be more than 0, then we will be able to conclude that X dominates A because of this constraint, that each of the members have received at least as much utility as it received previously.
Yes. This is same as the first option of this problem.
Yes. So this is the correct ILP formulation, whereas this one is not completely specified. This is only partial representation. So this formulation is correct, whereas this formulation is not correct. So in the assignment of which is due on Wednesday, there is a slightly different ILP formulation, but because uh, we have discussed how ILP formulations are made for this problem, I hope that you will be able to parse that ILP formulation and answer the question. So let's move ahead. So here is an interesting question. So in fact, there is one more question, but let us see. We'll probably do only one question today. Another question. So yeah, so okay, so we have already understood the definition of fingerprint and NP freeness. So there are some statements we have to answer whether these statements are correct or not. So maybe this will take more time. Maybe we'll look at the smaller question. Maybe this is easier. So what do you want to do? Do you want to go beyond 1 hour? Then we will also look at the other question. If you want to stop at 1 hour, we'll just look at this question. It is simpler.
So I'm fine with all the options. Let Shivang answer.
Okay. Shivang, so I'll check this chat. It generally types on the chat box. Shivang, are you there? Okay, so I'm not sure if it's there, but let's do one thing. Let's do this question first. So let me write it down if it's back. So do we want to go beyond 7 o'clock today? Okay. Yeah, so in the next 5-6 minutes, we can finish this question, then we can decide what we want to do. Okay, so let's read the question. Okay, so yeah, in the previous class also we have seen that the vertex cover problem can be represented as an integer linear program, but then the integer linear program itself is an NP complete problem. So we said that, okay, we cannot solve it in polynomial time. So why not relax the integrality constraint and allow fractional values? Saying something. All questions are not covered. Cover the first question only. We are doing the second question. So if you're fine, then we'll do another question after 7 o'clock. So does that work? Okay, fine. This is open. Right. So let's go back to this question. So the thing is, if we have the linear programming relaxation for an integer linear program, then any uh, polynomial time LP solver can solve that. But then we will get fractional values for the LP variables, and that doesn't help us because we are in the domain of integral values. So we are asking questions like uh, how many vertices are there in the minimum set cover, or in this case, we are asking that how many objects of this type shall we allocate to this person, and how many objects of this type will allocate to the other person. So it is interesting to see that if we formulate the integer linear program, then we can do something useful with the integer linear program. So there is a question called integer linear program feasibility. So it basically gives you an integer linear program and then asks that whether you can find a solution which respects all the constraints. So feasibility means it is not optimizing the objective function, objective value. It is just respecting. So that is to say that all the constraints are satisfied. So a solution that is such that all the constraints are satisfied is a feasible solution. So once you are given an integer linear program and we're asking the question that whether there exists a feasible solution or not, that is the integer linear program feasibility question. Like in this case, so if somebody can give us an allocation and says that, okay, So you allocate. So maybe you give the camera to this first person, you give the guitar to the second person, you give the mic to the third person, item to the fourth, item four to the fourth person, radio to the third person, and notebook to the first person. So this is a valid allocation, but we do not know whether this is the best allocation. So any valid feasible allocation, any valid feasible solution is the integer linear program. Feasibility is an ES instance for the integer linear program feasibility question. So now they are asking the question, an ILP feasibility instance with n variables and m inequalities is polynomial time solvable in if n is, so we know that if n and m are not bounded, then this is an NP complete problem. But if the question is if n is bounded by a constant, then is it possible to give a polynomial time solution? That means it is possible to give some allocation to this n variables such that all the m inequalities are satisfied in polynomial time. So that is the question. So we have a relaxed problem. And the thing is, so, so what is the objective function? So we are minimizing or maximizing something. So we are minimizing or maximizing. Let us say, so the number of variables is strictly less than 100. Oh, sorry, at most 100. So it's a function of x1, x2, let us say 100 variables. And it is a linear program. So it is a linear function. So linear function in the sense there are no quadratic or larger powers of any variable. So all the variables have degree 1. So subject to there are linear constraints. But how many constraints are there? The inequalities are there, m inequalities. And each of these inequalities are in this 100 variables, at most 100 variables only. Okay. So can we find a feasible solution? That is a question in polynomial time. So polynomial in n and m. So basically n is constant. So basically we are asking whether there is a poly m algorithm or not. Polynomial in m.
Yes, so if I view this as a vertex cover problem with a given upper bound on the number of the vertices, and so in the last meeting we discussed that the solution of the vertex cover would be of the order of say n square multiplied by 2 raised to the power n. So if the value of n is fixed, so then it would be a large number, but then it would be a constant. So therefore, the answer of this would be yes. It would be tractable.
Yes. So even if there are so many, let us say there are exponential number of, so we do not know. Maybe m is 2 to the power 100. I mean, not. Yeah, in this case, n is 100. So maybe m is so large, as large as 2 to the power 100. So then also we are saying that, okay, we are asking for a polynomial time algorithm in m. So if m is 100, then polynomial in m is also 100. So we have the liberty to have a lot of running time. So as soon as the number of variables becomes constant, is bounded, then we can solve this in polynomial time, as rightly pointed out by Mr. Coyle. Okay, so next one is simple. So suppose you are given an integer linear program feasibility question. So you are given a program, ILP, and there exists an assignment of these variables such that all the constraints are satisfied. In that case, that kind of an ILP instance is called an ES instance. So it is saying that any solution corresponding to an ES instance of an ILP feasibility problem is also an optimal solution to the integer linear program. That means it also optimizes the objective function. So you consider any feasible solution that is also going to optimize the objective function.
So this is not necessary.
Yes, because there are so many different possibilities out there. For example, even if you consider the vertex cover problem, So we want to minimize the number of vertices, and the constraints are on each edge, that for every edge you take either one, at least one of the two endpoints. So if you take all the endpoints, that is a valid vertex cover. That is a feasible solution. So you have a graph and you take all the endpoints, and that turns out to be a valid vertex cover, but that is not a minimum vertex cover. So therefore, an ES instance is not necessarily an optimal instance. So we'll mark this as false. Okay, now let's move to the next one. So any solution to integer linear program instance is in the set of solutions for integer linear program feasibility instance. So the feasibility instance means that this contains all the feasible solutions. And the ILP instance has probably a couple of optimal solutions. Maybe there are multiple minimum vertex covers in a solution in a graph. So it is asking that whether every minimum vertex cover is also a feasible vertex cover. That is the translation of the question in terms of our language, in our language.
This is true.
Yes. Of course, I mean, if something is optimal, in the first place, it has to satisfy all the constraints. So that is a given. So because it satisfies all the constraints, so any optimal solution is in fact a feasible solution of the ILP. So this is true. All right. So this was a simple one. So that's why I thought that we'll do this. So it is 7 o'clock, 4 past 7 now. So we have one question. So this one we can do in another. It is not very small questions, a couple of statements. I think this will take 20 to 25 minutes. So let's do one thing. We'll take a break for 5 minutes. Then by 7:30 we can wrap up. Let's break for 5 minutes now. So I'll give you a minute or so to read the question.
So can you summarize this NV free thing once again? What
Okay.
was it?
So envy free means that nobody feels jealous about another person. So let's read it. If no agent prefers any other agent's bundle, bundle means set of objects that a person has received, the box which we are saying, more than his own. So envy free means, let us say, consider person one. Let us say person one received a guitar, and the person one, I'm just making this up. Let us say he has received a mic and he has received a notebook. Okay. So for example, let us say that he values only guitar and notebook as one, and for mic he has no preference, so he doesn't like the mic at all. So the utility that he has obtained is 1 plus 1 is equal to 2 under some allocation. That is correct.
Yes.
So let
Yes.
us say there was a person who is person 2, and he has, so let us say person 1 also liked camera. So let us say person 2 has received a camera, and he has received a guitar, and he has received a mic. Okay. And he likes all these items. So his utility is 3. Let us say there was a person 3, and he liked so he whatever he liked. So he got a notebook, he got a camera, and he got a guitar. And let us say that he didn't like many of these things. So let us say he didn't like a guitar, he didn't like a camera, he only liked a notebook. So his utility is only 1. Okay, fine. So now after the allocation is made, after the allocation is finalized, so person 1 gets to see the allocation of persons 2 and 3. So person 1 realizes that he has received an utility of two objects that he likes, but he realizes that if the person two's bundle has been given to him, he would have got one utility from the camera, one utility from the guitar, and nothing from the mic because he doesn't like the mic. So he would have still got 2 utility. But if he were given the bundle corresponding to person 3, he would have got one utility from the notebook, one from the camera, one from the guitar. He would have liked to have this bundle. So he would be jealous of person 3. So that kind of a allocation is not N50. So N50 means whatever the person has obtained, in his evaluation, he has got the best utility because every other bundle is worth equal or less than what he has obtained in his perception.
So if an allocation is not NV free, then how can it be an optimal solution? Uh, so there could be a possibility that in the allocation, which is so called an optimal solution, the person one may not be having a utility more than 2 in all the allocations, but then the person one can always look for having some more utility. So I mean to say that if an allocation is not NV free, it cannot be an optimal solution.
Okay. It depends on, so yeah, so that is your definition. So if you define optimal this way, that we want optimal with the constraint that it has to be NV3, then that is true. For example, in this question, we are looking for an NV3 Pareto optimal, Pareto efficient allocation. That means they want that nobody should be jealous of anybody else. At the same time, it should not be possible to have another allocation which is NV3 at the same time dominates the given allocation. So they're looking for an allocation which cannot be dominated and is also NV3.
Okay. Okay.
Yes. So here, let's read the question once for being self-contained. An allocation is called NV-free if no agent prefers any other agent's bundle more than his own. Given an input of n agents, m goods, and agents having utilities ui. So for every good, an agent has an utility which is some integer, need not be 0 and 1. So that is a set of integers. And yeah, so every agent has this thing, utility. The EEF problem, that is NV-free efficient problem, asks if there is an NV-free and Pareto efficient allocation. We call F to be the set containing fingerprint Fi for a good GI. Fingerprint we have already seen, this is formally saying. So we call F to be,
Your voice is breaking. Yeah.
okay. What might be the reason? Let me check the mic. So the mic looks to be okay.
It's okay now. It's okay now.
Okay. So both the mic and camera are fine, right?
Camera is not fine. Camera, your video got freezed, but yes, audio is coming fine now.
Oh, video has frozen. Let me check the internet connection then. What is? Let's do some speed test. I'm receiving quite good speed. I don't know why the camera has frozen. Is the camera still frozen?
Yes, yes.
I can try restarting the camera. So I restarted the camera. Now is it moving?
No, it's black now. I mean, nothing is visible now.
Okay.
Yes, now you are visible, but then nothing is moving. So it's a very stationary frame.
Okay, fine. So as long as the voice is good, let us go ahead.
Yes, yes.
Yes, so we have seen what is the definition of fingerprint. So for every object, you consider the set of people who like that object and call that the fingerprint of that object. So if you have, how many members you have? You have n agents. So there are n agents. So you consider an n-sized vector. So in this n-sized vector, you have ones in the positions where this item is liked by the corresponding agent, and rest of the entries are 0. So that is a fingerprint corresponding to an item. So ith item fingerprint is f sub I. Okay, that we have seen already. So fingerprint definition is fine, right?
So, like, what's the meaning of F3 then?
So which all, so let us say the item 3 is, let us say item 3 is guitar. So let us say the person 1 likes the guitar, so that corresponding one. Then person 2 doesn't like, so then we have 0. Person 3, let us say, likes guitar, so like that we will obtain a vector of length n, so that is f3.
Okay, yes, clear.
So the number of goods having fingerprint f is mod f. So if So we consider this vector. So if there is an identical vector, let us say there is another item, let us say item 5, which is the notebook, and every exactly the same set of people who like the guitar also like the notebook, then the corresponding fingerprint for notebook will be identical to the fingerprint of the guitar. And for a given fingerprint, we count that how many objects or goods have the same fingerprint. So we denote that number of goods having the same fingerprint as hash f. Okay.
Yes, so just because the value of f is same is not necessary that the fingerprint has to be same, because quite possible so the number of ones could be same, but then their location could be different. So
We
quite
are
possible.
we are
So guitar,
comparing the. Go ahead.
yes, yes. So guitar and say the mic could be liked by the 5 agents, but then quite possible that guitar may be liked by the first, fifth,
Okay.
and the second one in that way.
Then the guitar and mic will have different fingerprints because the vectors will be corresponding vectors will be different.
Yes, yes. S-
So you understood what is a fingerprint.
Yes.
So now you can try this one. Question A. Let's mark it A, B, C, D. So Z is the number of distinct numbers appearing in the utility matrix. So utility matrix is what? Remember the utility matrix. So let's go to the. Okay. Shall we go there? Okay, let's go there. So this is the utility matrix we have seen in the beginning. So in this utility matrix, the utilities were either 0 or 1. So the number of distinct integers in this utility matrix was only 2, 0 and 1. But it can happen that the utility matrix is not binary but integral. So there could be many different integers in this utility matrix. So let us say that. So the question is asking that if there are z distinct numbers appearing in the utility matrix, then how many fingerprints are possible at the max?
So for the first location, we have z number of the possibilities, and since the
Yes.
length of the vector is n, so there would
Yes,
be z raised to the power n number of the possibilities.
exactly. So that is correct. That is true. The second one, given an EEF allocation, EF means is NV free at the same time Pareto efficient. That means cannot be dominated by another allocation. So given an EF allocation, if two goods with the same fingerprint are exchanged between two agents, then the modified allocation may not be Pareto efficient. So let us take an example. So let us say that. So let us say that the guitar and the notebook are liked by the same set of people. Okay. So, so let us say that this is the column for the guitar and this is the column for the notebook in the utility matrix. So this is the guitar and this is the notebook. This is the column for the guitar, and they have the same fingerprint. That means in every row they have identical entries. So if there is one here, there is one there. If there is zero here, there is zero there, like that. Now the guitar is allocated to. So let us say there is an agent A. In the box of A, there exists a guitar and certain other things. And there is an agent B. In the box of B, there is this notebook and certain other things. So we are following the same convention. So A is the box of agent A and AB is the box or bundle of agent B. So A has received a guitar and certain other things. B has received a notebook and certain other things. Now, if we do a swap, we do an exchange, the person A says that, look, you can take my guitar and I'll take your notebook. And person B says, all right, you take my notebook and give me your guitar.
But then the utility of the guitar and notebook would be different. So even if the fingerprint is same, the final utility is going to differ and may not be Pareto efficient.
Yes. So there is an utility matrix and the utility matrix is integral. Just a second. The battery of the pencil is dying. Okay, so what does Pareto efficient mean? Pareto efficient means that uh,
So,
this one does not
but
dominate.
but then this question, this yeah. So this is option C, and I cannot see the option B clearly. Can you slightly scroll it up a little bit? Yeah, yeah. So then they are asking that may not be Pareto efficient. So that would mean that the utility should be either equal or greater. So the entire utility. So the entire utility thing means that so if we change this thing, that the utility of individual agent may differ, even though the total utility may remain the same, because their fingerprints are same. But yes, so but since the utility of individual may differ, so it cannot be Pareto efficient.
Now, first of all, we are given an EF allocation. So the allocation that we had was Pareto efficient and it was also NP free. Okay. So now that means that there is no way to dominate this allocation. Now we come up with a different allocation. So in this allocation, there is one exchange. So the exchange is between two agents. And if the utility matrix is binary, so consider the case first when the utility matrix is binary. That means the utility for guitar is either 0, 1, the utility for notebook is also either 0, 1. Then because of this one exchange, the utility of agent A and agent B does not change.
Yes.
So maybe the utility of agent A was 10. Now guitar is replaced by notebook, it is still 10. Similarly, the utility for, let's say, agent B was 12, it remains 12. So in case the utility of guitar and the notebook are binary, then there is no problem. And the Pareto efficiency will remain. But if guitar is valued differently than notebook by person A, then his utility will decrease. That is not a good idea. Then the Pareto efficiency will be lost. So I do not know what is the assumption. So if the assumption is so that it's a binary matrix, then of course we will go with this option. Otherwise, we'll go with this option. So it depends on, it is not clearly stated what is the matrix. In the answers, NPTEL is saying that this is the answer. So maybe they thought that this is a binary uh, utility matrix. All right.
So I have a question here that if an allocation is NV free, it is necessary to be Pareto optimal. But if a allocation is Pareto optimal, it is not necessary to be NV free. Is this correct?
So you are saying that Pareto optimal implies NV3.
No,
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 no.
no.
You're saying,
NV free implies Pareto optimal.
okay, so let me write it down. So you're saying NP3 implies Pareto optimal, and you're saying that Pareto optimal does not imply NP3.
Yes.
So NP3, NP3 means that nobody likes the other person's bundle more than his own bundle.
Yes. So if everybody is happy in a society and nobody is envy of anybody, then clearly the things are optimal. But if the things are optimal, maybe because of some conditions, because of some constraints, then it is not necessary that everybody is happy.
That I understand. Informally speaking, that makes sense. But how to formally justify it, I'm trying to think. Pareto optimal means that there is no way to dominate this allocation. No way we can improve the quality of solution for somebody without decreasing the quality of somebody else. And this would mean that this may not mean NP3ness. Yeah, that makes sense. Okay. Okay, so maybe there is a way to formalize this, but in the face value, it looks right to me. I cannot comment for sure.
Yes, okay. Because there could be potentially there could be some violation in a situation which right now cannot be visualized.
Yes, yes. Okay. Not sure. But I can look it up. It won't be very, I think it is all explored. We can check it out. Okay, so let us move to the next one. So we're looking at D. So let XIF denote the number of goods with fingerprint F allocated to agent I. So agent I has received a couple of goods of the same fingerprint. For example, in this case, if agent A had also got a notebook along with a guitar, then uh, with this fingerprint, agent A has got two objects. So XI, this fingerprint would be XA, this fingerprint. So let us say this fingerprint is called F. So XA of F would be 2 in this case. So the statement is then an allocation is NV3 if and only if for any two agents I and I dash, this thing holds. So what is this? And let us parse this. I and I dash are two agents. F of Y, what is F of I? So F is a fingerprint, F of I.
So they have used I for two things. Here I stands for the agent, for two agents I and I dash. So f of I is for the agent I,
Yes.
fingerprint of the agent I, and XIF is the number of the goods with the fingerprint F to the agent I. Yes. So I mean the left hand side is related to the agent I, and the right hand side of the inequality is for the agent I dash.
Yes.
So and this F is the element of the capital F. So yeah, so the number of the goods multiplied by the fingerprint is greater than the number of the goods and multi. So what could be the meaning of the number summation of this F? So what this capital F here is?
So capital F, let us say, is the set of all fingerprints, distinct fingerprints.
So do we need to carry out this summation over all the fingerprints? Is this
Yes. The finger summation is over all fingerprints.
or possible
Now,
fingerprints? Yeah.
yes, now every agent has been given his box. So we are looking at all the distinct fingerprints in his box times f of I. So f of I would be uh, fi, that is, I'm slightly concerned. So what is fi is not well defined because fingerprint is defined for objects or items. Let me just try to make, you know, make a guess about what they might be trying to say. So I don't know. I don't immediately see what is the meaning of f indexed by I. We'll just, anyway, so we have partly solved the question. So this will, I don't know how to answer this question. So they are saying this is true. We don't know why it is true. I don't understand what is fi. Leave it. We'll just move ahead maybe because the notation itself is not clear to me. So for the binary 0, 1 utility matrices, the NP-free Pareto optimal allocation problem admits an FPT algorithm parameterized by the number of agents. And the second one is saying that EF problem admits an FPT algorithm parameterized by the number of agents in case of integer utility matrix. So I think in the book it is there, not in the book. In the videos, for the binary utility matrix, they have shown an FPT algorithm parameterized by n number of agents. Here, a number of agents is small n. Okay, so this is true. So NPTEL is marking this as true. This is either is from the videos. This is false. So this one we do not know, and this one depends on whether the matrix is binary or integer. Okay. So this is all I had planned for today, and I think this is sufficient for the assignment. I think
It took
deadline on.
almost, yeah, it took almost 2 hours.
Yes, yes, yes. Unfortunately, it has taken a lot of time. But yeah, we're not rushing through at all. Just making things, taking things slowly.
Yes.
All right, then I'll share this with you. I'll see you on Friday.
Yeah, sure. Thank you so very much, and thanks for organizing this extra session that too on Sunday evening.
Yes, yes. The match is also going on. I don't know what is
Yes,
going
yes.
on in the match.
India is one. Yeah, the score
Okay.
was it was a low score match.
Yeah, I saw that they were 50 something at 8 wickets down. What was the target? I don't know. Let us see.
51.
Okay. Okay. All
Yeah.
right.
Thanks. Bye.
Okay. All right.